I'm going to do it through R, but you're not confined to R. Most of your programming languages have versions of this now. Python actually has two. Python has Stan, which I'm going to use in R here, and also has its own kind of internal Python framework called PyMC3, which basically implements the same kind of technology as... okay, we're starting off on screen troubles. All right, so before we kind of move on and talk about kind of the more practical stuff, I'm going to give a very quick introduction to what is Bayesian statistics and how Bayes' rules works in 5 minutes, which is pretty much impossible. But instead what we're going to do is learn about Bayes' rule in 5 minutes. So is everyone here familiar with Bayes' rule? Conditional probability? Anyone not know what it is? Well, that's good. We can go through this pretty quickly. So Bayes' rule is that for discrete events. So you have two events, A and B, that are different. And what we're saying is that the probability of observing A, conditional on having observed B, is just the same as the probability of observing B given A times the probability of A occurring divided by the probability of B occurring. Okay, and that just comes from basic statistical manipulation. But it is actually quite a powerful thing. And that, for those of you who were at my workshop yesterday where we talked about the low base rates and we had, a small percentage chance of being sick just given the population as a whole, and then you had a test to check for the disease. Given that you tested positive, what was the probability of actually being sick? And the way to solve that analytically is just through an application of Bayes' rule. So it's fairly straightforward stuff to do. But the big question is, how do we use this? So the key thing and one of the reasons why I like Bayes and the Bayesian approach is that our brains are Bayesian inference engines. So the way our brains work is Bayesian, essentially. So what we do is we have an idea about the world, about something, and then we observe data. And then depending on how strong our belief was, we change our opinions about that. So if you have very, very strong beliefs about something, which you tend to see in politics, for example, right, it doesn't really matter what evidence you collect, you're going to need an incredible amount of it to start changing your political affiliation. Right? So we see that in America now, that kind of the president is defying all sorts of political norms and still getting away with it and still having quite a large popularity within his base, because basically they just don't really care. They have such strong beliefs in that they like his guy that it doesn't really matter how much evidence they get to the contrary. They kind of preserve the beliefs. And you see the same thing on the Democratic side now, okay, with all the Harvey Weinstein and stuff like that. So that politics would be one very good example where you have incredibly strong prior beliefs. So it doesn't really matter. You just need truly phenomenal levels of information to start changing those. Okay? So, I said we just don't know it. So it shows us, it basically tells us, well, how does that process occur? So we know that kind of once we have an idea and then we have data and we combine the two, we end up with a new opinion. Bayes' rule basically talks about how we do that. So when we get new information, we're going to, update it. So we're going to start with coin tossing. Okay? Now I hate the word coin tossing because I always end up saying toin tossing. Right? So if I do that, please notice and just tell me. Especially when I've given quite a few workshops and lectures about this kind of stuff, and I've tried to stop talking about this purely because I keep saying toin tossing and it gets very embarrassing after a while. Right, so the basic idea is we have a coin and we believe that that coin is fair. So from a mathematical point of view, what do we mean by a coin being fair? We basically say that the probability of getting heads is about 0.5. That means it's roughly a fair coin, because the chances of getting heads or tails is pretty much equal. Okay? So from a mathematical point of view, that's kind of our prior belief, that the probability of seeing a head is 0.5. Okay? So this is our initial belief. Now, what we're going to do, we're going to actually test it, like we did in the interests of science at the start there. Okay? which is great now because I have a belief that of my possession of magical powers is 1 based on 2 pieces of evidence. So that's great. So we toss a coin. We get a heads. Is it fair? Yeah, seems pretty reasonable. Let's do it again. We get a head again. Is it fair? Yeah, pretty much. I mean, it's not that unusual to see 2 heads in a row. We get 3. Yeah. Okay, but it's now kind of 4. So we now have 4 heads in a row. Yeah. But we're starting to get a little bit, maybe not. A little bit. 5th, heads again. Okay. And so on. Yeah, probably not. We're getting 6 to 10 in a row. We get 11 to 20 in a row. So we've now had 20 tosses of the coin and we've had 20 heads in a row. We're going to say, nah, time to call BS on the belief. Okay? So the chances of it are 1 in a million. So that's Bayes' rule being applied. Okay? That's how Bayes' rule works. It's all it is. You're just, you have a prior belief, you're collecting data, and as more and more data comes in, you're updating your prior. And what's been happening there is that as we've got more information, our belief that the coin is fair is getting smaller and smaller. Okay? And Bayes' rule allows you to quantify this qualitative process. So, let's look at it again. So that's the rule, that's the formula we have. Okay? So we're going to simplify it down. We're going to we kind of ignore, in most cases, right, we don't care too much about this B thing because that's the data we've observed, usually. Okay? So we don't care about this probability. This becomes like a normalizing constant that is often quite difficult to calculate, and we kind of ignore it. And it doesn't really affect our inferences on what we really care about. So we care much more about this kind of, what these inferences are here. So we can generally save ourselves a lot of time and avoid that particular calculation. And we just say that that's always constant as well. So this number is proportional to this, so we tend to just focus on the right-hand side. Okay? Oh, by the way, I should say, I know it's a relatively small room. By all means, if you have any questions or you want me to go over something again or explain, just ask away. Okay? We've got quite a bit of time. So, let's break it down. So we have PA. So this is the probability of seeing A. That's our prior belief. So it represents what we believe is the state of the world before we really do anything. And it's known as the prior distribution. Okay? And then we have this probability of B given A. That's known as our likelihood model. And it's what updates as data arrives. So we update this part of the process. Okay? And then the probability of A given B is the posterior distribution, and it's our updated beliefs. Okay? And most of these calculations involve trying to calculate this posterior distribution. Right? And that's what allows us to make any statistical inferences we may wish to make. It's the posterior distribution. Everything that we do from that comes from some calculation involving the posterior. Okay? So, a picture is worth 1,000 words, which is generally true. Anyway there. So now what we have here is a little web app, which I'm going to use. So, can everyone see that? I know the screen is a little bit. So what we have here at the top, I'll just move to the computer here. So what we have here is distribution parameters for our prior belief. So what we're seeing here right now in blue, this is a probability distribution for the probability of seeing heads. It goes from 0 to 1. Well, you can't see 0.9, so 1 is up here. And what this is saying is that most of the probability mass is between, say, 0.3 and 0.7. Right? So we're saying that the chunk of our belief is somewhere around 0.5. Now, we don't have a very strong belief that it's actually 0.5, but there's quite a lot of it here. Okay? And in reality, of course, when you're dealing with physical instruments, it's never going to be exactly 0.5 anyway, because you're always going to have tolerances around that in terms of manufacturing and so on and so forth. So we believe that, but what we're really saying is when we believe that the probability of getting heads is 0.5, what we're saying is that it's this very narrow region around 0.5. Okay? So what we have there is the prior. So this is parameterized by these two parameters up here, alpha and beta, which I know some of you can't read particularly. Hold on, let me see if I can zoom in a bit. Is that a bit better? So we have an alpha and beta. So we can see we've got a bunch of stuff here. And then we can just tie in our results of the tossing a bunch of coins. Okay? So let's say we have 20 heads. This is giving what we just observed in the slides. So if I calculate that, so what I'm doing here is, and some of you would have seen this yesterday, what I've done here is, this is my prior distribution. We collected 20 data points, all of them were heads. And what this is telling us, this is our posterior distribution here, and it's telling us that the probability of getting a head is now very, very unlikely to be 0.5, and it's much more likely to be up here in the, say, 0.65 to 0.9 region. Now, we haven't said it's 1. We're not saying it's always going to give us heads, because we had quite a bit of belief at the start that it was fair. And now that we've had 20 pieces of evidence to tell us otherwise, it doesn't actually tell us that we still believe it's 1, right? But it does say, yeah, it's probably up around 0.8. Okay? Now, if we tried that other, just to kind of show you, when I mentioned before, these distributions up here represent our strength. So what I'm going to do is I'm going to change that from 10 to 100. So now what we're saying is we have a much stronger belief that the coin is fair. And I'm just going to calculate all that. But we have the same heads. So we had a much stronger belief that the coin was fair. So we had a much tighter distribution around 0.5. And then we took 20 tosses of the coin. And now what's happened is, even though we've seen 20 heads in a row, we've a much less, we still actually have quite a strong belief that 0.5 is the true probability. Because we had a really strong prior, so as a result, we need a lot more data. Okay? Now, the other way, if we go back to, say, 10 and 10, let's say instead we collect much more data. Let's collect, say, 100 heads in a row. So you can see now we're pretty confident that it's basically virtually certain that the chances of a head is not quite 1. You'll never quite get there, but it's very, very close to 1. Okay? Because what's happened there is we have a relatively weak prior and we have a lot of data. So what's happening here is the data is kind of swamping, is overpowering the prior. Okay? Everyone got that so far? Now this is all on GitHub. If any of you want to play with this or anything, or play around with it, just give me a shout at the end. I'll give you the URL. I think I pushed everything up last night, but there might be a couple of things that aren't. And you can just play around and see what different effects it has and trying things out. Okay?
May I ask you a question?
Yes?
What was the goal for you showing this? To demonstrate how the Bayesian Rule works?
And also the interaction between the data and the prior.
If I understand correctly, if
Yeah.
we assume the coin is fair,
Yeah.
it does not matter how many times we see, like it will be 20 or 50.
Yeah.
That, then it should be again, probability should be again 0.5.
No. So when you have your prior belief, right, it's also representing the strength of your belief.
Okay. I try to understand what you say.
Yeah.
But there is a law of the large numbers.
Yeah.
Because I know, if I know that the coin is fair,
Yeah.
and I see the heads, when
Yeah.
I toss the coin 20 times,
Yeah.
it does not hurt my belief that the coin is not.
Well, what will happen there, but what you're saying there is if you have certainty,
Yes.
then the prior will be a Dirac function on 0.5. So it will have essentially infinite probability density on a single point. Right? And that means that no amount of data is going to move it.
That's what I understand.
Yeah. But you see, in the real world, that's involving infinite numbers. In the real world, when you're dealing with finite numbers, you're never going to have that. What you can have, so to say your point, let's say we put an incredibly strong prior on it. I'm hoping this works. And 20 heads. Okay. I think the red is in there as well.
Yeah.
Right? So what's happened is we essentially have a Dirac function on our prior. So we are basically saying we believe with 100% certainty that the yeah. So what's happening here is no amount of data is making us change. So the posterior and the prior are the same.
Yes.
What's the formula behind this calculation?
Basically.
It's just Bayes rule. So
It's just a Bayesian.
Bayes rule in continuous space, which I'm going to talk about. It's basically updating. It's the conjugate prior for this is the beta distribution. So what happens is you have the alpha and beta, and what you do is you add the number of heads to alpha and the number of tails to beta. So what you're having here is essentially whatever that is, a million. You have 1,020,000 and 1,000,000, and it's basically giving you the same answer. Okay. Any other questions? Does that make sense?
I have a question.
Yes, shoot.
Sometimes some gamers believe that today he have luck.
Yes.
Or not.
Right. Yeah.
That's why you are sure that it's 0.5.
Yeah.
Why you are sure of it?
Oh, I'm not. The one thing I've learned on this stuff is to never be sure of anything. So I always put priors around everything I do. And I'm not saying that because I'm trying to weasel out of being nailed to anything. I've just learned that certainty doesn't really exist in this world. So like it doesn't really matter how certain you are of something, you're always going to have some kind of distribution of beliefs around it.
You see, there is serial of something like these heads,
Yeah.
one by one. Yes?
Yeah.
I checked this one is the cars in the city.
Yeah.
For example, odd or this one. There was serial, a big serial.
Yeah.
These all are odd.
Yeah.
For example.
Sure.
And it's another serial.
Yeah.
Not that mixed.
Yeah. Well, you see, the thing is, though, what will happen is if you look around, when you look at large samples, you're always going to find weird things within them. And what humans do is we're trained to look for those patterns. So we see patterns in noise all the time because I think the most convincing theory of it is just evolution. That basically when we were like back in the countryside and basically afraid of wild animals, we kind of learned that that pattern over there might actually be a wild boar about to burst through and kill us. So we've kind of learned to be hypersensitive to patterns, and that's also why you start to see people seeing Jesus in toasted cheese sandwiches and stuff like that, and they think it's a miracle, so they start.
It's overfitting, right?
Absolutely. It's absolutely overfitting. It's also why like an awful lot of people think they've found the secrets to the market and they're going to make millions on the stock market because they've noticed this pattern, right? We are kind of hardwired to see patterns. So I think that's mainly, I mean, sometimes just weird stuff. I mean, there is the other one of like the birthday problem. Are you familiar with the birthday issue? So if you get a room of 29 people, I think it is, there's a greater than 50% chance 2 people will share a birthday. They'll have the same day of the year that they share a birthday. And that's just purely 1 in 365 and to the power of 29. And the other way around, 364 over 365. So I think that's probably what's going on there. Okay. Any other questions? Right. So that's the basics of it. Oh, I might have to. One sec. Oops. Oh. I went back. Hold on.
Sorry, are statisticians really separated in 2 groups, Bayesians and frequentists? Or
Okay.
just
Okay. I'm going to get to that now. Right. So, back when statistics was first kind of being developed in the early 1900s, so Bayesian Statistics is called Bayesian Statistics because there was a Church of England reverend in the 1700s called Thomas Bayes, who basically wrote some stuff on it, and he created what he was calling inverse probability. Now, it wasn't him who really developed most of the theory behind it. That was actually done by Laplace, who was involved actually in the French Revolution, and he worked with, I believe it was Napoleon, and he was like involved in artillery, and he basically invented Bayes as a way to improve artillery targeting and stuff like that. So the idea was, okay, we'll set it at this angle and fire it this direction, and it kind of landed close to where we wanted to get, so let's tweak it a bit. And he did that way, but somehow someone in the English world knew that the Reverend had said it first, so he kind of got his nib in, and that's why it's called Bayesian statistics rather than Laplacian statistics. Now, what happened from the historical point of view was the leading luminary in statistics, at least within the English-speaking world. I mean, it may be different in the Russian world, but in the English-speaking world, there was a guy called Ronald Fisher, who developed most of the kind of theoretical underpinnings of statistics around the 1900s. And he had a protege called Neyman, I believe his name was. And the two of them, they very quickly fell out and hated one another. But they pretty much created most of what we learned about modern statistical frequentist. The only thing they agreed on was that they hated Bayesian statistics. That was pretty much the only thing they could agree on. And they pretty much sabotaged an awful lot of work for it. So it became almost because their main argument was this thing that we talked about here is they don't like the subjectivity inherent in the prior. So they believed that essentially with the priors, you can fudge a lot of things and it wasn't objective. Now, the counter argument to that is that they tend to focus on the prior, but your choice of likelihood is equally subjective. I mean, when you're working on something, we're just making the assumption that a binomial model is a good one for the chances of a heads, right? Now, it's a reasonable approximation, but it's still just a choice of likelihood. So the choice of a likelihood and a prior is equally subjective generally. And the way you tend to work it in reality when you're dealing with priors is that you're generally trying to have relatively weak priors that are kind of somewhat informative in terms of what you already know, but they're not trying to fudge the answer. And in general as well, in a lot of cases you have a lot of data, so the prior just gets taken away, and it's really the choice of the likelihood. But the choice of a likelihood in Bayesian statistics is exactly the same as the choice of a likelihood in frequentist. So there was a big debate in the 80s, but what happened was then, and the other big problem was that a lot of this stuff was quite hard to do because it involves high dimensional integrals, which I'm going to talk about in a few minutes. And it just wasn't very practical. But as soon as it became practical, people realized it was useful. And once people realized it was useful, the philosophical arguments somehow became less important because it worked for people. So, and that, practicality trumps principle in a lot of cases. So you don't really have those debates anymore. Basically because in a lot of cases it works and it gives similar answers to frequentist too. The other thing I much prefer about Bayesian statistics, and one of the reasons why I got onto it, was I actually find it a lot more interpretable. As I was discussing yesterday, I didn't really start learning statistics properly until my mid-20s, and I immediately got this menu of statistical tests that I could never figure out when. I kind of understood what they were doing, but I never really understood, okay, well, if I get a real world problem, how on earth do I know what test to apply? And it just seemed to I had to learn off a whole load of menu of things, and I really, really hated that. Whereas kind of this framework provided me a somewhat infrastructure that I could just kind of apply to everything. Now, I'm sure a lot of people, especially now that this is going out on the internet, I'm sure I'll get a flurry of messages on Twitter telling me I'm a very bad person. But, that's the joys of the internet these days. So using these kind of simple building blocks, we can build some quite powerful models. So now I'm going to talk a little bit, which I've been trumped a little bit by this, but why do I like Bayesian statistics? Well, the main reason I like it is the interpretability of it. So it gives you a very natural interpretation. It's how we think. So a credibility region versus a confidence interval. You've probably all heard of confidence intervals in frequentist statistics. I still find it hard to explain exactly what a confidence interval is. The only thing I can say with a lot of belief is that it isn't really what you think it is, right? So a confidence interval is basically, if you calculate the 90% confidence interval of a parameter, it's basically telling you that if you make multiple samples of that parameter and calculate the 90% confidence interval for each separate sample, it will contain the true value 90% of the time. It doesn't tell you that there's a 90% chance that the value is in here, right? It's this other thing involving sampling multiple times, and that they're not the same thing. Whereas in the Bayesian world, that's exactly what a credibility region tells you. It tells you that there's a 90% credibility that the true value is contained within this interval. Now that interval doesn't have to be continuous, it could be separate ones. You could have a multimodal posterior or whatever. But it does kind of give you a much more... Now, that doesn't necessarily mean it's true, of course. It's just saying you what the model is saying. And there's no guarantee that the model is correct. Right? It doesn't solve that problem. You're always going to have that. A model is just a model, which is just a model. And it's not necessarily representative of reality. But it does give you a good way of testing the value. Because what you can do is, you can actually try it out and see, well, if I know the true answer and I generate data with my model and then I recreate it, am I actually able to recreate the values I had at the start? And do I get it 90% of the time? And if I do, then I know that at least my model is at least well specified, which is sometimes a problem in a lot of cases where you create some data, then you use the model to rediscover the parameters, and you can't actually rediscover them properly. And that's a good sign that your model is borked and you need to do something new. Okay, so that's one. The other thing I really, really like about this kind of stuff is it gives you a very natural way of dealing with hierarchical models and dealing with sparse data problems, which goes back to a couple of questions people were asking me yesterday about small numbers of categoricals, lots of categoricals with small counts of each. So you don't have an awful lot of data. So what you can do very simply, you can do this in kind of the OLS world as well, but in the Bayesian world, it's relatively straightforward to build these hierarchical models where even if you don't have a lot of data points in one particular area, but you do have a lot over here and you know there's a connection between the two, you can borrow strength. And it basically what happens is it tends to reduce the problem of sample size that you often get with small sample data. And it gets used in a bunch of things like, for example, insurance and banking, it gets used for risk pricing, pricing loans, pricing insurance, pricing derivatives, all that kind of thing. Multi-touch attribution is a big one in marketing that we're starting to see more and more of. So there was a StanCon last year. Stan is the software I'm going to talk about shortly. And there was a bunch of talks. It was a one-day conference. A bunch of talks were talking about this. So this is the problem in marketing where you have a website and someone sees an ad on the TV and then they see an ad in the paper and then they see one on one's website and then another ad on another website and then they go to the website and buy it. Right? And somehow you can tell that they know all this, but you're not quite sure, well, which channel of advertising was the one that had the biggest impact on this customer so that we can start improving our marketing spend. So we're starting to see that get used in, and they're using kind of Bayesian hierarchical models to do that. Another one is account segmentation. So you have all these different lines of business and some of them are mixed and you have maybe corporate clients or whatever. And then you're trying to figure out which ones are the most profitable and which ones aren't. And account segmentation, they use this. That's another use I've seen of it. And in the scientific world as well, we see a lot of it now. It's getting used a lot in ecology and geophysics and a whole bunch of other applications. StanCon is online on YouTube, by the way, all the talks from it from last year. It's very worth looking at, although the quality wasn't great and it's all one big video. I don't know if they ever actually cut it up into separate talks yet. But it's very good if any of you are interested in this. There's some really, really good talks on there. And some of them are quite basic as well, so it's a good place to start. Oh, and there's a typo. Never mind. Okay, so the Bayesian approach. How does it work? Okay, so this is the continuous form of what we saw earlier. Okay, so I've changed the notation slightly, and this is what you tend to see when you're using Bayesian data analysis. This is kind of the notation. So you have D, which is the data that we've observed, and we have theta, which is a bunch of parameters that we want to discover. So for example, if this is a linear regression, this theta here will be all the parameters of the linear regression. Okay? So p theta is the prior distribution for the parameters, and p theta given d is the posterior distribution. This is what we're calculating out here. And then, as I said, this integral here is the likelihood model. So it's the likelihood times the prior. So it's the probability of seeing the data we saw given some random set of parameters, and then this is being multiplied by the probability of seeing that set of parameters. Okay? Anyone got any questions? No? Okay. This will make a bit more sense, hopefully. So, like I said, we ignore this. The data is always the data, so this probability calculation is expensive and not really necessary, so we ignore it, and we just focus on the proportionality equation. So, how do we calculate it? So it basically boils down to calculating this integral. Okay? So how do we do that? Now, your big problem is that it's very, very high dimensional. Okay? So this, for example, it's very easy to have thousands of parameters if you have a big hierarchical model, right? But even if you have a very simple regression with like 10 features, that's a 10-dimensional integral there because you have 10 different parameters that we're trying to integrate over, okay? So how do we calculate them? Now, as we discussed yesterday, the curse of dimensionality kicks in, and it's a big problem in like one way of doing this will be the equivalent of grid search. So what we do is we take the 10 dimensions, we split them all up into like, we discretize it in each direction, and then we calculate in each little cube that we have, we calculate the integral and then we add them all up, right? The big problem there is that scales exponentially. And as everyone knows, if anyone who's done any complexity theory, exponential scaling is terrible. So anything beyond really 2 or 3 dimensions, when you try and discretize it up, it becomes totally infeasible to run, and you just end up waiting forever to even do the simplest of integrals. So anything beyond even 10 dimensions would be probably beyond supercomputers in any kind of real world problem. So we need something else to do. So luckily, there's been a lot of stuff on this. So what we use for calculating the integral is a whole bunch of other technology. And you can't really see this thing, but Stan is the one we use, and as I mentioned, there's PyMC3. But essentially we take a simulation approach. So the curse of dimensionality works for us in this point, right? So as I mentioned to you before, yesterday, with the curse of dimensionality, does everyone here understand the curse of dimensionality? I recognize a few faces from yesterday, but I may need to go over it. So basically, as you add more and more dimensions, space gets more and more empty. So what that means is when you're running these, if you do it like brute force and discretize everything, you end up calculating 0 probability in most places. So it's a complete waste of computation and you don't need to do it. What you're trying to do is somehow select the areas of non-zero probability and just sample from them and calculate the integrals in those areas and add all those up. So there's a whole bunch of probabilistic ways and importance sampling and stuff like that. So what Stan does is it uses Markov chain Monte Carlo, which is one particular method of doing these integrals. And what it does is it uses a Markov chain to simulate from one place in the probability space to another. And then you kind of move along them and you're sampling them roughly in proportion with the probability density that you care about. But on top of that, so they've got the sampler, they've got a probabilistic programming language that makes it very, very easy to build probabilistic models. And it's built on the back of a C++ backend, so it's quite efficient. And there's a truly excellent online community. They're incredibly helpful. In fact, sometimes they're too nice, because there's a couple of people that come on the Stan forums and they're basically saying, please do all my work for me. And sometimes you feel like telling these people to, well, let's just politely say, go away. And they actually deal with almost superhuman levels of patience, which at some point, there's 1 or 2 individuals online now that are actually becoming comedy. It's like, oh, great, he's posted again. What's he got to say this time? Yeah, it can be quite. Now, the technology behind this is pretty impressive. So what it does is, I haven't really mentioned it here, but it uses Hamiltonian Monte Carlo. So what that does is it uses physics simulation. So if you think of your probability density that we're trying to calculate as a hill, right? What it does is it uses physical simulation. So if you imagine a ball on that hillside, and it gives it a momentum, and then it calculates that trajectory. And the idea is that that physical simulation allows you to track both the potential and the kinetic energy. And the potential energy is the equivalent of the hillside and the height. And then it allows you, from doing that, the trajectory of the particle allows you to basically, the idea is it's moving around the hill, given a certain speed and a certain velocity. And that allows you to kind of track its movement, and that kind of maps out the surface of the hill, which is our probability space. So it uses some pretty cool physics and some very clever statistics. And it's been built by, to put not too fine a point, a bunch of geniuses out of Columbia University. Some very clever guys. And it's very, very cool. But the one thing I'm going to ask is, why are we going to bother with all this stuff? Right? I mean, I know I talked about it briefly, but what's the point? I mean, like I said, this is all very well and good, very fancy, very clever, but there is the danger that you're just doing something cool because it's cool, not because it's actually practical. And that's certainly, for anyone who's like me, that's always a trap you try to avoid, but it can be quite often. So you'll just do something because it looks cool, but actually you could just calculate a mean and a standard deviation and then you could be done. and you don't really need to go with your fancy Gaussian mixture model that takes a week to run. So why bother? Well, it captures uncertainty very well. So one of the things that you get in the output of the Bayesian approach is that you get a posterior distribution. You don't just get a point estimate. So what happens is it actually captures all the uncertainty inherent in whatever model it is you've built. Now, it doesn't capture the uncertainty involved in the model error, as in if your model is wrong, but within the framework of your model being correct, it actually calculates all that uncertainty. So you end up with distributions of values at the end rather than single point estimates. And that can be very, very handy, especially if you're dealing with skewed distributions. So if you've got stuff that you know has a very skewed output, right? The expectation only tells you one thing. The maximum likelihood point is probably wrong because it's generally lower or higher than the values you care about. And it also we're naturally programmed to think in terms of nice symmetric distributions. So if someone gives you a point estimate and an error, you kind of naturally think of it like a nice little Gaussian curve. But in reality, what happens is that you might have this mad skewed distribution, and your expectation, like you've got this big long distribution that has a big long tail, and your expectation is here. So if things go badly, right? So let's say it's a loss amount or a cost, right? If things move against you, they're going to move against you pretty hard in the bad direction. Whereas, and not very much in your favor if they move in the good direction. So it's very important often to get a sense of the distributions of these outcomes as well. And you just get that naturally as part of the Bayesian thing, and it comes in a relatively coherent way. It tends to be very easy to iterate and improve upon. So once you've actually built your model and you've got a relatively simple thing up and working and you're happy with it, but you need to start to add some changes to it, it's generally reasonably simple to do that once you kind of understand the coding. It allows for generative modeling, which is a big, big thing for me. So a generative model is you're actually generating the data from scratch. So what you're doing is, rather than trying to come up with some model and then model the data, what you have to think about is you stop, you take a step back, and you think about the underlying data generating process that may have generated the data that you're trying to analyze. And you're almost like trying to reinvent the wheel, but in a good way. You're kind of saying, okay, here's this data we've seen. What do we know about how this data came about? Let's actually try and build that model and then make inferences based on that generative model. And that can be a very, very powerful way, especially when you've got weird types of data, like truncated or censored data, or missing parts of it, and all that kind of stuff. You can actually build those kind of wrinkles in your data set right into your model. Now that is reasonably advanced stuff, but it does actually enable those kind of advanced techniques. And then finally, as I mentioned before, hierarchical modeling for sparse data. So, now, this isn't a magic bullet. There are quite a few pitfalls in it. The learning cliff here, there's quite a bit going on. If you've heard of a learning curve. Some of the Bayesian stuff can have a bit of a learning cliff, so it does go a bit like that. Now, it's not a hugely steep cliff, but there is quite a bit at the start. But they have, particularly the Stan guys, and I believe the PyMC3 guys, have made quite a lot of effort in making it very accessible to new people. So it's quite easy to get started now, and then you can kind of go back and backfill once you kind of know what your problems are. So, and that's one of those things, getting started is one of those things I'm going to talk about in a little bit. There's quite a few things involved. It requires aspects of physics, computation, and statistics to kind of understand what's going on. It's reasonably easy to blow your toes off and not really know what you've done wrong. So it can seem a bit overwhelming. But I honestly believe it's well worth the effort of putting in, if only because you actually learn an awful lot more about basic statistics once you kind of get into it. And I found that that's just been very valuable in general. Because one of the key things I like to say is that real life tends to present basic statistical problems in new and unusual ways. And that still happens to me today, where you're looking at something, you're like, what is that? Oh, that's actually the central limit theorem in a really weird way that I'd never thought of before. So that sort of thing. So kind of understanding the basics, you could never learn that too much. Oh, okay, so we're going to get started. I'm going to start with a very, very simple linear model. So is everyone familiar with linear regression? Anyone not? So basic linear model. So what we're going to do is we're going to implement a linear model in Stan, in the Bayesian framework, and so the idea is I'm trying to do something that's fairly simple in terms of modeling and then show you how it works in the Bayesian world so that you're at least not starting from completely new. So, linear models. So, the general way we go is we have some basic setup. We have input variables x. It's parameterized by beta. And we use our formula here. Y is our target variable. So we have this kind of linear algebra. Y is beta times x plus some error, where we have error being distributed normally. Okay, nothing particularly weird there. And what we tend to do is, there's a whole bunch of methods for this, but the standard one is to use ordinary least squares. Maximum likelihood is the same. And you essentially have some kind of matrix transformation. You do it a bunch, and you solve a bunch of linear algebra, and you get your answer out. And the answer is like the maximum likelihood estimate of those beta parameters. Okay? That's basically what's going on. And you have a constant variance sigma for the error. So we're assuming that regardless of what data points we're putting at, we always have the same kind of fundamental noise that we're not capturing in the model. Okay. So what we're going to do now is we're going to rethink the linear models in a Bayesian language. This took me a little while to get my head around. So we need a probability model for it. Before I, sorry, because I've been blathering for an hour now. Does anyone have any questions or everything okay so far? Okay. So we need a probability model for this. So this is kind of inherent in when we build a linear model. The theory of linear models has all this in it. It's just that when you deal with linear regression, a lot of this theory gets kind of hidden implicitly. And another reason I really like the Bayesian world is it's very explicit in terms of your assumptions. Basically, all the assumptions that you have to make in your modeling, you kind of have to program into the model. Whereas when you're using an awful lot of kind of pre-baked algorithms for a lot of this stuff, there is implicit assumptions that get talked about in the textbook, and then everyone kind of forgets about them later because you don't ever really have to think about it anymore. And that can cause problems later on. So whereas in this one, everything is very, very explicit. So what we're assuming here is that every data point, right, so for any given set of input values, the output variable is going to be a normal distribution. And what we're trying to do is fit the mean of that normal distribution. Okay? So for every single data point, we can think of it as being sampled from a separate normal distribution, where the variance of that distribution is constant, it's this sigma, but the mean of it has been calculated from this particular formula. So we have a set of beta variables, and then every data point has its own set of x values. We're going to do this kind of multiplication and addition, and that's giving us the mean of our distribution. Okay? And then we're putting that in the middle of the normal distribution. So this here, this equation is equivalent to this one here. What's happening here is rather than having this error, we're basically putting this beta x into here. Do you see that? So, we've got a very simple claims model. This is a talk I've given before, so again, I'm using insurance. But this is all data sets that are available in BaseR, I think. It's the insurance data, the auto BI. So I've changed it around a little bit. So what we've got is we have a bunch of data for claims. So it was claims that were made in some policies somewhere. And we have, I think in the US, and there's a few features. This is kind of offset a bit. So we have whether or not the person had hired a lawyer, if the person was male or female, whether or not they wore a seatbelt, and what age they were. So those are our input features. And then we have a claim amount, but to try and get it continuous from minus and positive, we're fitting the logarithm of the loss. All right? Now that's a common technique you get. In linear models, you can't really force linear models to be positive. So a common way is if you've got zero bound values, you just take the log of it and then you fit the log. Okay? Now there are implications for that for the modeling. We don't have to worry about that too much here. Okay? So what we're doing is we've got a standard. Are you all familiar with formula notation from R? It's used in Python as well. So what's this saying is we have a linear model where the log loss is the target variable and the parameters are lawyer, seatbelt, gender, and age. So we're going to fit a parameter for each of these. Okay? This one's continuous. So this is a number. These are all categorical, and I think they only have 2 values, either yes or no, or male or female. So we're just going to be fitting a single parameter for these. So our total, it's going to be a 4-dimensional problem, right? And this one is continuous. It's going to actually multiply the age. Okay? Right. So everyone's familiar with that, I'm assuming? Yeah? So how do we do this in the real world, in like standard R or Python with OLS models? Can everyone see that? It's a little bit small. So we have model LM. So we're fitting it with a linear model. Log loss tilde, lawyer, seatbelt, gender, age. We pass in the data, which I have as model data.tibble. And that's the table that we saw in this previous one. And then we're going to fit the model. So we haven't done anything Bayesian yet. I'm just showing how it works kind of in a way that you're probably most familiar with. And then this gives you a whole load of bunch of things that you can apply in R, plot out the outputs. It gives you like, checking the residuals, QQ plot to see how good the fit is, all that kind of stuff. You get all that stuff, right? So that's all very well and good. So now we're going to do it in the Bayesian world. So we need to set up this model in Stan. But there's quite a bit of effort involved because we need to create that predictor matrix, and we need to set up the beta and set up the linear algebra. We need to do all that within Stan. So thankfully, some of the guys that do the Stan in the Stan world have created a package called rStanArm. ARM stands for Advanced Regression Modeling, which for some reason is what Andrew Gelman calls his book that I mentioned yesterday, Data Analysis Using Regression and Hierarchical Multi-Level Models. For some reason that got brought down to ARM. So rStanArm is basically based on that, and it has a whole load of pre-built models that are like standard in R and like standard models, but they're pre-built, they're written in a relatively optimized way, built for speed and all that kind of stuff, and they have a few other bells and whistles. So it works for linear models, for GLM, ANOVA. They're actually starting to look at survival analysis. They're looking at time series as well. Yep.
This survival analysis was my question.
Yeah, I'll get to that after. That can be done in this as well, yes, but it's a little bit trickier because it's censored. Yes, it is. It's not been implemented yet in rStanArm directly, so you have to kind of code it all up yourself. But yes, it is possible to deal with that. I'll talk about that right at the end, because that's one of the things I've been looking at. I've never had a chance to. Oh. Okay. And the idea is it's built for easy use. Okay. So how does it work? Well, we have this stan_lm that comes in the package. We're going to run it now in a second. I'm going to switch over to RStudio just to show you how it works. So you can see it's almost the same. We have the formula here, we have the data, but now we've had to specify a prior. Okay? And there's all sorts of different priors you can set on your parameters, like normal distribution around them, whatever. For some reason that gives you problems which I won't get into right now. I'll get to it towards the end if I have time. So we've set this what's called the R² prior. So the Columbia guys have found that a very effective way of fitting these models is to put a prior on the R² of the model. So the R² of a linear model. So what this is saying is that we expect this model to fit with 0.8 of an R². And that somehow, I've never really figured out how the R² prior works, but it essentially puts some implications on the parameters themselves. It doesn't actually mean that the model will fit with 0.8, but it's just got some parameter for it. And that makes the model work. Okay? So what does it look like? So here's our outputs. So one of the issues you have to deal with when you're dealing with Stan is your sampler runs and it creates a posterior sample, but you have no idea if that sample is correct or not. Okay? We don't know, and there's no theoretical guarantees that the sample that you've sampled from the distribution is actually the posterior distribution you were trying to sample from. So all we really have are kind of rules of thumb and diagnostics that we can create, because it requires this kind of technical thing called geometric ergodicity, which essentially means that it doesn't really matter how far along you are in the chain, the underlying parameters don't really move much. And calculating geometric ergodicity is basically impossible theoretically. So all you can really do is test for it empirically from the data. Right? So one of the common ways of doing it is to use what's called, is to look for what's called mixing. So the idea is you run multiple chains. We've got multiple chains here. So do you remember I mentioned earlier that the particle gets simulated, right? So the idea is what you do is you have multiple chains of simulations that start in different areas of the probability space, and they all wander off and start exploring it. And the idea is that if they're doing the right job, they'll all end up in roughly the same area. And when you plot any given parameter across all the different chains, once it's properly mixed, you'll start to see this, what they call the hairy caterpillar. So what's going on here is all the 4 chains are kind of mixing around the same particular value. About 0.8, I think that is it? 0.5. So that's about 0.5, and there's 4 chains in there. Unfortunately, with the screen, you can't quite see it. There's 4 different colors in there, and they're all kind of mixed in together. So that's a good diagnostic. It's not perfect, and it's not definite, but that's a good indication that you're at least on the right track. So the sample that we've created is a sample we want to work with, right? And that's telling you that this particular value, which is the intercept, so the intercept is around 0.5, okay? The next value, which is a lawyer value being yes, that's around 1.3 to 1.4. The next one over here is yes for a seatbelt, and that's about -1. So if you didn't have a seatbelt, the claim was lower. This one here is male, gender, and then age. And this one's much smaller because this gets multiplied by the age. Okay? So this is kind of giving us a good idea that what we've sampled is actually what we wanted to sample. And what we can do is we have, say, 2,000 draws from the posterior distribution. So we can plot like density plots for each parameter. So we can see here, there's what's our uncertainty in each of our parameters based on the data we have. Okay? So these are relatively wide. Well, this is 0, this is 1. So you can see there's still a reasonable amount of uncertainty around what the intercept value is. Similarly for the lawyer, and similarly for all the different parameters. So we can see now that we haven't actually done anything new, we just fit a linear model, but already we have a much better sense of the uncertainty, right? Now this is the bit where I find it very useful. So we have 2,000 samples from our parameter space, right? So what we can do is, if we're trying to predict from the model, or as a way to test the model, right, we basically use a particular sample and a particular set of parameters, okay, and then we basically create the prediction from the linear model. But unlike when you fit it in the OLS world where you have a single point estimate, so you get one at value, now we're going to get a distribution of predictions. So what we're saying with our model isn't telling us that, the claim size for this particular person is this. We're saying it's actually a distribution around that. Okay? And you can see in this case it's a nice kind of normal shape. It doesn't necessarily have to be, it could be skewed depending on how the parameters are set and how much correlation there is between them. Okay? So what I like about this though is, so we have this black line here is the distribution of predictions given the output of the model. Can everyone see why we're getting a distribution here? Do you understand that? So if we've 2,000 samples, right, for any given claim, we're going to have 2,000 different estimates of how big that sample was, of how big the claim was, because we've 2,000 different parameter sets that we pass through each claim. So we end up with this distribution of claim sizes for each given claim. Okay? And what I've plotted here is the maximum likelihood estimate is the red line, and that's always like the mean, the expectation of the distribution in these cases. And then we have what the observed value is. Okay, so this is just actual versus expected. So in the OLS world, we would just have the red and the blue line, and we can see in some cases they're relatively far apart. Okay, in some cases they're very, very close. Right, so it's not necessarily a bad model. But you also start to see that this model in the Bayesian world is probably better than you would think it is, because even though in some cases the observed value is not very close to the red line, which is the MLE estimate, it still lies pretty strongly within most of the distributions. So we're not seeing like a blue line that's way out here in zero space. Do you see that? So what's happening is that we can kind of now there's ways of checking it. For example, you would probably want to make sure that 10% of these predictions are estimating about 10% of on the probability space, right? So you check for the credibility for that. But we can see here now that this model is actually not doing too bad a job, because we're now allowing for the fact that there's uncertainty in the parameters in the model, right? So it means that A, we're less confident in these predictions, these red line predictions, but we have a much more realistic view of where we are in the world, right? Because we're not really saying, I believe this number is going to be the prediction. We're now saying, well, the prediction is distributed around here. And to me, that's always a much more, like I said to someone when you asked me earlier, do I believe something? Life has taught me to never believe firmly in anything. I always try to put distributions around my belief, because that tends to be the way the world is. Unfortunately, a lot of people don't like that, because they want that kind of certainty of an answer. But whenever possible, I try to explain that that's not the case. That doesn't always work. Sometimes it fails spectacularly, but there's not a lot you can do with that. Okay. Any questions so far? Do you all kind of follow where we're going? Okay, I'll just show you how that works in practice before we move on to a slightly different example. So we have, which is the 8 schools problem, but up here are you all familiar with R, or at least a passing familiarity with it? So I've created some data here that I've got from the auto claims, which is part of insurance data. And I've just done a little bit of cleaning up, and the data was in slightly messy format, so I tidied it up and made it Boolean where it was. But this is the code pretty much that I ran the last time. So I'm just going to show you how it works. So you just get there's some new changes coming through. So what's happening is it's now running on multiple cores. So as I said, there's 4 different chains being ran. So they're running the into 4 different areas of probability space and then combining them all together. And what's happening here is it's just taking a little while to run. And what we should start seeing, unless the output has been captured, hold on, we'll start to see some outputs from the chains. I think that's is it down here? It doesn't take too long to run. Now, this is the one downside, is that these sampling, because we're not calculating one value, we're calculating 2,000 values, it does take a little bit longer to run. So what's happening here is we're running 2,000 iterations across 4 chains. So we're actually, we're going to end up with 4,000. We're running multiple chains. I think we have 4 of them. So it's running them all through now. So the first half of them are called warm-up, and then the second half are called sampling. What warm-up does is, as I said to you, it starts in random areas in the probability space, and it's looking for the typical set, which is the thing we discussed yesterday with like where most of the probability mass is. And the warm-up, there's a whole bunch of efficiency stuff that needs to be taken care of so that it doesn't take forever to run. And the first half of the iterations are basically a combination of finding the typical set and finding the optimal set of parameters to sample from. So it's kind of busy away doing that. And then once the first half of those, generally they split it half and half. So the first half is for warm-up and adaptation, and the second half is sampling. So once the adaptation is done, the warm-up ends, it goes into the sampling, and then it finishes. And you see it's done there. So it took a few seconds, and it took. The other thing that happens with STAN is that it builds a model in C++. So there's sometimes it uses automatic differentiation. So they had to build their own AD. Are you all familiar with automatic differentiation? Has any of you heard of that? So it's used for gradient-based methods. Does anyone here not know what automatic differentiation is? Don't be shy. Okay, so one of the things when you're doing optimization and kind of exploring geometric spaces in general, which basically most of modern day computation does these days, methods are much more effective if you know what the gradients are, because you kind of know what direction is uphill, is the easiest way to think of it. And the problem is an awful lot of functions are very hard to differentiate. So one of the reasons why we were very restricted in what models we could do was we could only really use functions that had easy to calculate gradients, so that we could calculate the gradients analytically and then program them in. And that was a huge source of bugs, because it was very easy to get those gradients wrong and very easy to put errors in the calculation. So what automatic differentiation does is it uses differential geometry, and it basically uses a combination of the functions and the compiler to basically look at the function, and then it automatically builds the derivatives from that as part of the compilations time. So that's a lot of what, like, a lot of the modern day machine learning packages that you hear about, like TensorFlow and all them, they're all largely frameworks for doing AD and automatic differentiation on top of that. And it's a relatively new development. I think people were talking about why isn't it used more often in the late 2000s for like statistics, because it's so useful, and it was just one of those things that hadn't really percolated across. It's been around for quite a while, but now kind of everyone's discovered it. So it gets used in MXNet and XGBoost and all them. They all use these kind of gradient methods to kind of just essentially run things much more efficiently. And that's also why we're seeing this big boom. It gets used a lot, for example, in backprop when you're fitting deep neural networks and stuff like that. It's pretty cool stuff, although some of the maths gets a bit hairy in it. It was all the stuff I had to learn as part of general relativity. So I'm going back trying to remember my push forwards and my pullbacks and stuff like that. But it is very interesting stuff. They couldn't do that. The Stan guys were looking for it, and some of the stuff, there was automatic differentiation libraries, but they weren't really built for probability distributions, so they had to essentially create their own. So Stan has its own AD library, which uses reverse mode differentiation. I won't bother getting into the technicalities of it. But it means that essentially because you need the gradients, in some cases you need the second order and the third order derivatives as well to do some of the physical simulation they're trying to do. And they just do that automatically as part of Stan. The downside to that is when you build your Stan model, the first thing it does is it creates a C++ program and it compiles it. And that can take quite a while because the AD has to expand out the expression trees and a bunch of things like that. And that can take, in some cases, really complicated models can take a long time. Most of the time, though, you're only waiting a minute or two. One of the big benefits of our Stan ARM is they've built a whole bunch of pre-compiled models. So you don't actually have to wait for those to be, they're pre-compiled when you install it. So when you run it, they load up the particular Stan model and they throw the data out and they run it. So we've kind of missed the compilation step here. Okay, so that ran. So what's the point? So just to show the trace plots, so we can go say, hold on, I'll bring it in here. What is it called? Oh crap, hold on. Sorry about this, hold on, I've accidentally deleted a bunch of things. There we go. So, that's fine. So trace plot model Stan LM. Oh, sorry. So this should give us the values. Just taking a little while. So this gives us a nice graphical representation of the parameters we fit. So again, unfortunately I can't, those are a bit small. So we have the intercept up here. So we can see there's quite a wide uncertainty of values. So the way it's set, the way the defaults are set here is, this is the 50% credibility interval, which means that if the model is correct, there's a 50% chance the true value is in here. This is the 80% credibility interval. So it shows the 50 and 80 together. They try to discourage the use of the really extreme values like 95 to 95 or 10 to 90, for the simple reason that they tend to be, there's so little data out there that they tend to be very, very prone. So they'll change a lot depending on the sample you take, whereas 50 and 80 tend to give you, are much more stable estimates and a lot less error prone. So that you tend to see 50 and 80 in the Stan world at least, rather than say, the 90% or 95 and 95. Okay, so that's why one of the things you'll see in finance is they're now focusing very much on the 1 in 200, which is like the 99.5 percentile. And one of the issues I would have with that is that you generally have very little data out there. So your estimates of like how bad things can get can be very, very sensitive to the samples you've ran. But anyway, that's a story for a different day. So we've got all these other parameters. We've got like the lawyer, seatbelt, male, insured, age, and then we have a few other bits and pieces they throw in there. We also have an estimate of the R squared, which is actually down around here. So even though we set a prior on it of about 0.8, our R squared is estimated to be about 0.3. So it's not quite as good a fit as we thought it was. And yeah, and now we have kind of a model, and there's a few other odds and ends that the Stan guys give you. There's also another package called Bayes plot, which has a whole lot of really, really nice plots for diagnosing your fits, using the outputs, all that kind of stuff. And then the final really, really cool tool that I like a lot is Shiny Stan. So if any of you are familiar with Shiny in R, Shiny is like a quick way of creating very simple websites in R, and you can kind of very quickly build simple apps for displaying your models. I find it a really good way to kind of, if I've built a model and I want to show it to someone, I'll build a very, very quick Shiny app that creates some plots that I want to do. And you can whip something up that looks reasonably okay in like half a day, and pretty much has quite a decent amount of functionality in it. So these guys, one of Andrew Gelman's students, Andrew Gelman is the main professor of all this in Columbia University. He's kind of like one of the main kind of, he's not the main kind of implementer, but he's kind of one of the guys who kind of leads the thought leader, I suppose is one way to phrase him. He had one of his students who's now on the Stan team. He created Shiny Stan, which takes a Shiny Stan fit and creates a website automatically that has all the diagnostic plots in it, helps you with posterior predictive checks, has a whole load of other like exploratory tools that allow you to explore the model. And it's really, really, and it basically just works. You load up Shiny Stan, you pass it the value, and it creates a little website for you on a local host, and it's really, really useful for doing this kind of stuff. And it means there's a whole lot of work that you don't have to do yourself. It's particularly handy when your stuff doesn't sample. I'm quickly running out of time here, so does anyone have any questions? I'm just going to talk very quickly about the 8 schools model, and then I'll leave it alone. No? Okay. All right, so one thing you'll see a lot of in kind of the Bayesian world is the 8 schools problem. So have any of you heard of this? Any heard of 8 schools? That's the data there. Okay? So the 8 schools problem was, I think it was originally it was a piece of data that was collected by some school district, I believe in the US, but I'm actually not sure. And it was, they had a whole bunch of tests that they gave pupils, and then they calculated the average difference between the base rate result of the test across like the state or whatever. And this school, so this is saying that this school had on average 25 points more than whatever the average was across the state, with a standard error effect of 15. So this is the 8 schools that had 8 different values, right? So all we have here are 16 data points. We have 8 means and 8 standard errors, okay? And this gets used a lot. This was actually, working on this problem is what motivated the creation of Stan, right? Because this was considered a really, really simple problem. The old samplers that were created using like Gibbs sampling and stuff like that were thought to be working very, very well. And then Andrew Gelman was working on it one night, I believe. This is the story I've been told. He accidentally left it running over a weekend, or he went on holiday. And he just left it running for like hundreds of thousands of iterations or millions of iterations for like a week, or over a weekend, or over Thanksgiving or something. And when he came back, he noticed there was, and then he looked at the trace plots. And when he came back, he noticed there was weird stuff in there. And it looked that even though they thought this model was fitting very well, it wasn't actually doing as good a job, because what was happening was, once you let it sample for long enough, it was finding regions of the posterior space that the sampler couldn't get into, because there was hidden problems with this that the sampler couldn't find and wasn't really able to diagnose. So that was kind of, they were looking to do something a bit better than JAGs, which is what people were tending to work on at the time. And that kind of motivated Stan. And at that point they were saying, actually there's problems with Gibbs, let's start using this other thing called Hamiltonian Monte Carlo. We think we can implement it now. And that kind of created with it. So I'm going to just show you very briefly the 8 schools problem, because working on this problem alone can teach you an awful lot, A, about Bayesian statistics, but B, and probably more importantly, the problems that you encounter when trying to take the Bayesian approach to do this. But it is very, very, and it uses hierarchical models and stuff like that. So the first thing I'm going to do is just plot that data. So actually I should have one made earlier. Hold on one sec. Sorry, wrong one. And again, this is both of these are online. Scroll up. So that's the data there. So what we've done is, let me just zoom that in a bit. Okay. So kind of at first glance, it looks like that some of these schools are much, much better than the others. So if you can see, this one here is like 25, and this one here is -5, or -2 or something. Okay? But what I've done here is I've just plotted the dot here is the mean value, and then twice the standard error. So I'm kind of assuming a normal distribution. So I'm assuming that like about 95% of the probability mass is within there. Okay? And when you look at it that way, all of a sudden the picture becomes a little less clear, right? Because even though the differences are very far away, when you start to account for the standard errors, all of a sudden there's an awful lot of overlap between all of them. Okay? And you'll generally find that. So what tends to happen is that when you take samples of data for things that are related, you will quite often get these extreme differences between the two. And these extreme differences are often somewhat misleading, because it's very unusual to see schools to have that stark a difference in effect, unless you're dealing with, schools in incredibly wealthy areas that have all the best teachers, and then, students in incredibly poor areas that were straight out of the wire, right? But even still, you would expect that somehow we should dampen this sampling effect. So what gets done is we basically treat this as a hierarchical model. Okay, so what we're going to do is, I'll just show you it here. So this is what a stand model looks like. Now we kind of, you got away with not seeing that before, but I'm going to show you it now. So we have the data that we're passing into the model. So we have J, which is basically the number of variables. We have a value Y, which is the sample, the mean, mu. And then we have a sigma, and we have 8 of them. So we're basically passing in 17 numbers, right? 8, and then the digit 8, and then 8 Ys and 8 sigmas, okay? So that's the data that Stan is going to expect to see, right? We then set up the parameters of the model. So these are the values that we're going to be sampling from. So what we're sampling here is, we're assuming that there's a mu, and then there's an underlying tau, and then there's a theta. So we're essentially saying that these 8 numbers, just go back here, we're saying that there's an underlying probability distribution for a school. So this is what we're calling like it's like a hyperpri or a hyperparameter. It's slightly different for hyperparameters in machine learning though, but a similar kind of idea. So we're saying that rather than treat these 8 things as 8 separate entities, we all know they're from schools. So what we're instead going to say is that if you know there is a school in general, what kind of averages can we expect to get from that school? So we're kind of putting a probability distribution over the 8 schools. So we have this distribution at the top that's kind of feeding into the 8 data points we've observed. Can everyone understand that? And then what we're trying to say is, given that this is what we've observed, what can we say about schools in general? What can we say about that hyperdistribution? So that's what that mu is, right? And that's the tau. So that hyperprior is the mu and tau. Okay? And then we have a real theta, which is, and then we're setting it up. So we're saying that the mu is a normal distribution, centered at 0, with a standard variance of 5. And then we have tau, which is a Cauchy distribution, which I discussed yesterday. And that's, we put a lower bound on it to be 0. So even though Cauchy goes from -infinity to +infinity, we've kind of put a constraint on it. So this is a half Cauchy. So it starts from 0 and only goes positive. And then we have a normal distribution for theta, which is mu and tau. And then we're saying that the y values are being drawn from whatever theta value is here. So we've got the probability distribution here feeding into 8 probability distributions down here. right? And these probability distributions are what we actually sampled from. So there's kind of two levels of normal distribution going on. I know this takes a little bit of getting your head around. Okay? And the idea is we're going to say, okay, well, given that we know these hyper values, what can we then say about mu and theta? So let's run that. What time is it? Time is almost up, so I'll tell you what, I'll run the later one. There's a problem with this model which I won't get into. I don't unfortunately have time right now. I was hoping I would. If any of you are interested at the end, we can talk about it. Actually, I'll just run it so you can see it. Stand model. So we're going to have to compile this model. I'll show you how it works, and we're going to run this. I've ran it already, but I'll just show you how it works. So what's happening right now is it's compiled it down. Oh, it had been pre-compiled. It's now sampling. So it's the same thing that we saw before. So what's going to happen is once it starts up and running, you're going to start seeing chains running. It shouldn't take very long because there's very little data in it. And again, like, it's taking all these data points, it's starting in random parts of space. Unlike the last time I had 4 chains and 2,000 iterations, this time I have 8 chains and 500. So I'm going to end up with, half of these are going to go away, so there's 250 samples in each chain, and I'll have 8 of them, so I'll end up with 2,000 samples from my posterior. So you can see it's running away now. It's not going to take very long. And you can set it up so that if you've got, you know, multi-core machines, 8 cores or whatever, it can run each chain on each separate one. Right, so this is the one kind of thing I want to mention this to be as a caution at the end. So we've got what are called here 33 divergent transitions after warm-up. Increasing it may help. It actually won't. There's a problem with the model here. And the estimated Bayesian fraction of missing information was low. So what's happening there is there's a problem with our model, right? And that manifests itself in Hamiltonian. So there's a problem with the model in general, right? And it's called, one problem you have with hierarchical models is that, I'll try and explain it here. So we have, what happens is, when you get, this is called a centered parameterization. So as we said, we had a probability distribution here, and we were sampling a mean from it that was going into another probability distribution down here. And the problem is, when you do that, there's always a chance, depending on the data, that your posterior space starts to look like this, and it starts to basically vanish down to a single point. And what happens there is, when it gets smaller and smaller and smaller, the sampler can't get into it. And that manifests itself as a divergence. What happens is, when you're doing the numerical simulation, you end up with essentially a crazy number, and rounding error kicks in, like you would get in physics, and you get this crazy number. And that basically tells you that the sampler is trying to get into this space of increasing curvature, and it can't get to it, and it basically tells you that your model is misspecified. Now, one of the problems that a lot of people have with STAN when they start up is they build these models, they immediately get a whole load of warnings, and they think there's a problem with the software. What the STAN guys have been very, very stringent on is they want to tell you when there's a problem with your model, because a lot of the other samplers didn't. And what happens is, you don't know if the problem is a big one or a small one. In some cases, it might not make much of a difference. In the 8 schools model, it didn't, which is why it got unnoticed for so long. But what Hamiltonian Monte Carlo tries to be as sensitive as possible to those kind of model misspecifications, and it warns you loudly about so. So there is basically ways of reparameterizing the model that I'm now past time, so I won't get into it. But it does give you the answer. So what I'm going to do is very quickly is run the centered model which fixes this, and then you can just see some of the output from it then. So I'm just going to plot those parameters. So we have, okay. So what's happening here is we have mu and tau. So this is the hyperparameter. And then we have the mu tilde, which is being sampled within this value here. So this is 0 here. Where is it? There. Okay. And then these values here are what are the ones that we're sampling from. And then these are the ones that we're seeing from the school. So we can actually see, when you look at it from this point of view, having sampled from a hyperprior, you can actually see there's much less of a difference between the schools than we originally thought. Even less so probably from having looked at the data, just plotted it by itself. Okay? So the idea was, this was seen to be saying that that school that was at 25 was just so much better than the one that was at -2. But when you actually start to bring in more information, like we know that the schools aren't that far apart, you can actually see that it kind of brings all these, it's essentially smoothing out that sample noise that we had before. Okay? So that's kind of, there's a whole bunch of stuff on that. There's a bunch of links. Hold on, I'll put it on at the end, because I'm now absolutely out of time. Let me just, I'll show it there for any of you who are interested in all these kind of, reading all this kind of stuff. I have, oh, I don't know if I put it up there. I have my GitHub repo as well. It's on the stuff if any of you have seen it before. If any of you don't have it, I'm sure the people will be publicising it as well. Yeah, so that's it. Has anyone got any questions? I'm sorry for keeping you a bit long. I know there's quite a bit to take in for this stuff. Personally, I think though, if you're interested in this stuff at all, these techniques are well worth starting to learn about. And they've, the STAN guys in particular, and I believe the PyMC3 guys. I know one of the core contributors to PyMC3, but I've never really used it, so I can't talk. I've used it a little bit, but not very much, so I can't talk at length about it. But my understanding is they've made it quite easy to use as well. They tend to take more of a machine learning approach, whereas these guys are much more statisticians. But I think, for example, the PyMC3 guys, if you're interested in Gaussian processes and stuff like that, they've put a whole lot of work in the last 6 months to make that much easier to do within PyMC3. Whereas the STAN guys have been focusing on a few other things. They're kind of creating STAN 3 shortly. But yeah, that's it. There's a whole bunch of good reading. Yeah, if anyone's got any questions, please come up with me at the end or grab me for the rest of the day. I'll be here all day. Oh, I did. Thank you for listening. That's my email. And if all this stuff is on my GitHub repo, pretty much all of them. This stuff in particular, the most recent versions may not have been pushed up yet. They will be by the end of the day, and certainly by the weekend. Okay? Thank you very much. Thank you for your time.